So our third and final speaker is Staffen Berg from Mentor Graphics in Europe, specialising in digital functional verification tools and methodology. He's been with Mentor since 1989, working in many different fields, including real-time software development tools, simulation, logic synthesis, formal verification, hardware, software, co-verification. Prior to joining Mentor, Staffen worked as system engineer at Redec and as EDA tool developer at Ericsson Telecom. Staffen holds an MSc degree from the Royal Institute of Technology in Stockholm in Sweden. And Staffen is going to talk about automating SoC-level tests with portable stimulus. Over to you, Staffen. Thank you.
Thank you, Mike. Thank you for inviting me today, along with the two other leading companies in portable stimulus technology, which is the topic of this presentation. The two previous speakers have already mentioned the Accelera working group in progress, and I'd just like to mention that Mentor Graphics is also a driving member participating in this work that's been having a lot of attention recently. So you have probably seen quite a few of these block diagrams already today, so here's another one. A typical modern SoC fabric that can have hundreds of different interfaces grouped into different clusters, dozens of different masters running transactions concurrently, and on top of it software running on these different cores as well. I think we all agree that methodologies like UVM and constrained random stimulus generation have been proven to be extremely productive and effective in IP or block level verification, but unfortunately many people have found that they don't scale really well when you move from IP level verification up to system or SoC verification. And the reasons for that are quite well known. The previous speakers have already touched upon it, that when you get this kind of system with all the concurrency, the total state space becomes simply too great. There's too many things going on at the same time. It's really impossible to just try and generate all types of transactions to cover all the different scenarios that you're interested in. You need to do a more top-down approach, start to think about which are the scenarios that are interesting, not just the transactions or sequences of transactions. Most of our users designing SoCs today don't use simulation alone. Typically we see usage of different verification platforms along the flow. People start maybe using something like System C for early prototyping. They move on to traditional RTL simulation, emulation, prototyping, and even post-silicon verification. The verification environment has to address all these different phases. Typically we also see many different languages, not just a single language. Maybe you start with System C for virtual prototyping or performance analysis, and then later on during the implementation phase, System Verilog is used, our software-driven verification using real embedded software running on processor cores. So to manage all this complexity, you must have a lot of automation to remove manual translations, manual steps, and you must have a high degree of reuse, both vertically and horizontally, as we have seen during the previous presentations. So if we take a step back and look at what are the elements needed for a complete specification of stimulus, regardless of the environment, the way we see it, there are two things that are needed. The first step is the entire legal test base, the blue circle that you can see on this slide here, which models the whole legal universe, every possible transaction or combination of transactions that are possible, including unexpected cases that the verification engineer maybe didn't think of. Now, typically for an IP or a block, this may be also your target that you're trying to cover, because it's reasonably sized. You can actually generate all the transactions to get full coverage. But on an SoC, that's simply not feasible. So the second element that's shown here is the actual targets, the scenarios that you're interested in during this particular test. You select the areas of interest. What is the focus of this particular test that you're going to run? Now, please note that this is different from a directed test. We are not specifically modeling exactly what's going to be tested. We're not saying do A, then B, then C. Rather, we are saying that, okay, we're interested in particular combinations of A, B's, and C's. But for now, we don't care about D and E, so they can be left randomized. And that way, we can systematically target the verification goals that we are specifically interested in. And this can be done essentially in 3 different ways. I guess this is the a similar slide to what Larry was showing about the different ages of verification. So first we have a traditional directed test where someone sits down and writes a specific test that does A, then B, then C. Typically this doesn't scale very well because someone has to write all the tests, so even if it's accurate, the productivity is not very good. So that's why more than 10 years ago people started looking at letting the computer do the tests by randomly generating tests. So a single test bench can generate hundreds or thousands of tests. Random generation is usually very good at capturing the data aspects of the test, not as effective in capturing control flows. But it's easy to generate lots of tests in a short time, but it's also easy to generate a lot of redundancy because it's an open loop, so you don't really know if you're going in the right direction or if you're just repeating the same sequences again and again. So the third methodology here is the topic of this presentation, graph-based, goal-driven tests, which also share some of the key attributes of constrained random. There's a high degree of automation, but it's more flexible because you focus it on what you want to test. It captures both data and control flow, as we'll see in some example here, and the productivity is very high because it's goal-driven and it's highly automated. Now, in a real verification flow, you probably need all 3. So the graph-based tests alone doesn't replace the other 2 categories. In a real, what typically our users are doing is that they are still doing some directed tests to do bare metal testing, to bring up those simple smoke tests. Then they are doing intelligent graph-based tests to make sure they cover the important scenarios. But they also use a lot of random generation. And as we will see, the graph-based technology allows you to combine these 3 in the way that best meets your goals. So how does it work? Well, you start out by writing a description of your stimulus in a text file, a rule file that completely describes both the data and the control flow aspects. This rule file defines the entire stimulus space, so it's the blue circle that you saw on the earlier slide here. It's a highly compact and efficient way to describe the stimulus, so it's usually 1 or 2 pages of code for real design. This model is then compiled with a special model compiler, and after the compilation it can be viewed as a visual graph. And can be easy to review and share between different domain experts such as verification engineers, software engineers. It's not specific to a certain language or domain, so it enables a high degree of horizontal reuse in that respect. So the actual rules describes both data and control flow. So the data aspect is described using familiar data types like scalar, composite types. It supports inheritance, different types of variables. In addition to that, you can optionally specify data relationships using algebraic constraints like the ones you see on this slide here to the right. But there's also the control flow aspect, where you need things like definition of sequences of operations, choices or selection, repeat loops, etc. So there are a few basic operators that allows you to model the control flow easily. On this diagram to the right, you also see another interesting construct that is extremely powerful, called a branch-specific or conditional constraint. Is this gray-blue box you see on the right? This is an algebraic constraint which only applies in a certain context. So it gives you a lot more flexibility than in typical HVL languages like System Verilog, and it allows you to partition your scenarios in a very efficient way. Another very interesting construct is called an interface, and I believe this to some extent addresses the question from Bernard at ST earlier today. So an interface is really a way to abstract out the connection between the stimulus description and the verification environment. So this simply is the connection between your test bench or your verification environment and the graph-based stimuli description. So an interface is declared in the rule file, and it simply specifies that I have some inputs, which are variables that can be read from the DUT or test bench, and I may have some outputs, which are transactions generated by the graph. Now, this doesn't say anything about the implementation. So when you run your compilation, the actual interface gets implemented in different ways depending on your target environment. So, for example, in a UVM target environment, the interface might be implemented as a start item, finish item method call. If the target is generating embedded software to run on a processor, it might be implemented as C function calls to a library of driver routines. The second part of the description is the coverage goal, where you express what scenarios you're interested in seeing. And this can be either simple data values or combination of values, or certain sequences or combination of sequences. So you can use constructs like simple cover points or crosses of variables or sequences, and you can prioritize them, and you can combine random and systematic generation. So once you have defined a coverage goal, it will be systematically targeted, while you can leave other things like particular data and address values to be randomized. It can also be reactive, so the goals can adapt to the state of the DUT or the test bench. And by doing this, we can suppress the generation of redundant stimulus and typically achieve 10 to 100 times faster to coverage compared to random generation. There are a couple of other constructs that I'll quickly show you because they're used in the examples. So just like in most HVL languages, you can further refine your goals by dividing up big ranges into bins to make them more manageable. There's also something called a coverage constraint, which can be used to reduce the size of target goals. So here we have two variables with 16 possible values, and the cross of them will be 256. But the actual legal space is much smaller. Based on this constraint, it's only 120 combinations that we're really interested in. So how does this apply to an SoC verification environment? Here is a very simple or simplistic example of your typical SoC. It's a fabric that has a number of different internal and external memories. There are two CPU cores and two DMAs. So of course this is a great simplification. In any real SoC there would be dozens or hundreds of these cores, but this explains the application, and you can imagine how it would scale to a real SoC. So one reasonable goal here would be to exercise all the data path combinations. So we want to make sure that core 0 can read from both the DDRs and write to all the internal memories and so on. DMA should be able to read from all the memories and so on. And we may also be interested in the concurrency aspects. So what happens if core 0 tries to write to an address at the same time as DMA 0 tries to read from it, things of that nature. And there is also some constraints that are implementation specific, like DMA 0 cannot access internal RAM, for example. The DMA can only do word-aligned transfers. So how would you model this using rules and a graph? Well, the first step is to describe the transactions we're interested in. And in this environment, the transaction is a memory transfer that has attributes like source and destination address. There's an offset to start in different places of memory, and there's a size, which is not really that important. So the size can be divided up into larger chunks to make it more manageable. And we also use a constraint to limit the size of transfers to something reasonable. So this describes our kind of generic transaction in our little SoC system. Now on the right hand side you see our traffic scenario where we're going to use this transaction that I just declared. So we import it, and then I declare 4 interfaces. If you recall the block diagram, we had the 4 bus masters, the 2 CPUs and 2 DMAs. So we declare an interface for each one of them, and the interface has an output of type memory transfer. We declare 4 instances of the memory transfer. Then we have our constraints that you saw in the specification. We can only do word-aligned transfers. The DMA can't access internal RAMs. And we use bins to say that we don't really need to target every single different size. We just want to do one of each of the small sizes, and we don't want to divide up the rest of the address space into 8 chunks. And the whole scenario is then just starting the 4 different interfaces concurrently. So in a way this is very similar to a UVM virtual sequence. So this would then in turn start lower level sequences that runs in whatever target environment we're looking at. I'll show you some examples of that in a moment. Now the stimulus model that we have built is a complete and self-contained formal model of the whole stimulus space. So we can do some interesting analysis on it up front without running simulations. So the whole scenario, if we wanted to do every different size of transaction on every different data path, we would end up with more than 10 billion combinations. So that's simply not feasible of doing, at least not in simulation. So we want to reduce it, so we only want to target certain source and destination combinations, actually all of the legal ones, which is shown by this kind of purple box on the diagram, which is overlaid on the graph. And there are certain combinations of transfer size that are interesting in this particular scenario. And once we have set up our goals like this, we can do this kind of analysis that shows us that given these constraints and coverage goals, there are, for the size combination, there are about 20,000 combinations, and for source and destination, there are about 16,000. So that's a lot less than the 10 billions. So it's certainly something that we can target. Now, what about the portability? I think you can start to see the idea now that the stimulus model that we have created is totally independent of the target environment. There's nothing specific to a certain type of test bench or verification environment. So the stimulus model can be shared across domains from block level to SoC level, and the actual implementation is taken care of by this automated model compiler that based on this single stimulus model can output, for example, a UVM sequence or a system C model or some embedded code running on a processor. So the graphs are really independent of both the language that is used and the environment. They're self-contained, and they describe both the data and the sequence scenario, and then they're automatically mapped to be able to communicate to and from the different environments. So this enables us to reuse the same graph across these environments. You can start by creating a block-level graph that drives some transactions on an interface, and then call it from a higher level graph, which is also generating calls to embedded software functions to process those transactions. You can create a graph to drive a high-level C behavioral model, and then reuse the same graph to drive a UVM test bench. So in our SoC example, we could, for example, use this graph to target a UVM environment. The graph would be implemented as a UVM virtual sequence, so it would appear as any normal UVM sequence. It would then launch lower level sequences on the different agents, so we have replaced the CPUs and DMAs with the UVM agents that drives the interfaces. These lower level sequences could be either graph-based or they could be reused. They could be existing UVM sequences created at the IP level and then just being called from this scenario graph. Another use model would be to take the same graph, and now the interfaces will be implemented as C function calls. So they would call a set of library functions running on the cores, and these library functions could do programmatic transfers byte by byte between the memories, or they could program the DMAs to carry out the actual transfers. Another type of reuse is across different language boundaries. One thing we have been working with customers on recently is in the context of high-level synthesis, where excuse me, we would start with a high-level C algorithmic or behavioral model, which is intended to be synthesized into hardware. Typically, this would be verified in a System C simulation environment. So we could create a graph that drives our System C environment. Then, after synthesis, where we have generated the RTL model, the same graph could drive a System Verilog environment or a UVM test bench, but it would be the same high-level graph that would be reused to do systematic verification in both environments. So, to summarize, excuse me, the graph-based portable stimulus is a very productive way of specifying your input stimulus. It's based on familiar data constructs. We're not inventing an entirely new language. It formally captures both data and control flow. It enables very efficient execution of the model, typically 10 to 100 times more effective than random generation, and it's highly scalable, running in parallel on a simulation farm. It's portable across languages, across verification environments, and across the different verification platforms like simulation, emulation, and prototyping. So it truly enables reuse, and it's highly automatable. It enables you to import and reuse existing test bench elements such as constraints and sequences, and it allows you to do a lot of analysis upfront before committing to expensive simulation runs. So that's my final slide. I'm afraid my voice is breaking up a bit, but at this time I could take any questions.
Yeah, thanks, Staffen. I think we can see you getting more and more in need of a drink of water, so thank you for finishing. Any questions from Bristol? Yeah, there's one question here from Roger Shepherd.
I wonder to what extent the description that you're using to base this on is adequately constrained, because when you generate, for example, to C code to actually run on SoC, you will be doing a lot more activity than you've stated in your graph, and some of that activity may cause some of the scenarios you're interested in not to happen. For example, if you were interested in a cache behavior, it might be that your program caused a cache clash not to happen because the cache had already been emptied or something.
Yes, that's true that it's a kind of balance how much of the activity that is controlled by the graph and how much is controlled by the software that gets called by the graph. And I agree that in the case you described, there could be a lot of activity happening in the software that is outside the control of the graph and the coverage model. The use model that we are thinking here is that the software that gets called would be actual driver code for the real SoC, and the coverage would be at a higher level. The graph would just generate some transactions and then call the software, and this would be the actual software that's running, and the coverage would ensure that, for example, all different kinds of transactions have been generated and processed by the software. But what the actual software really does is not modeled by the graph. That's true.